Good. Thank you for being there. I'm going to explain topic 4. Thank you for being there. I'm sure you're going to have a good time here learning some stuff. Very interesting. So, here in topic 4, chemical changes in matter, what we're going to see is the different changes in the matter and chemical changes and how to recognize them. Okay, so the first thing we need to remember is this sentence here. I'm going to underline. Okay, so chemical change produces a new substance that did not exist before the change. Okay, so let's, for example, differentiate chemical changes from other changes. We have, for example, a phase change. It's not a chemical change. Yes. For example, when you boil water. Yes. So this is a change of matter, a change of phase. So we change from liquid to gas, for example, or dissolving sugar into water. That's not a chemical change, and no new compound is created. Okay, so how do we know if a chemical change is occurring? So there are some clues here. Okay, gas release. So when you're burning something, you produce a gas, for example, CO2. A new substance is created. This is the same matter. Yes, we had oxygen and carbon. Yes, as in a paper, for example, is like into the matter. But when you burn paper, the CO2 and oxygen, boom, goes out in a form of smoke. Color change. A substance from a chemical reaction might have a different color. Thermal energy exchange. All chemical changes involve energy exchange. So normally when we burn something, we need to apply some heat, and this heat is generating a chemical change. An energy release as light, yes, like a fire, yeah, or flames. And I'm going to focus on these words here. Many words are onomatopoeic, that is, that are formed by imitating a sound made of are associated uh, with that name. Okay, so it's, for example, a bubble. Yes, you know that is a burbuja, yeah, a bubble. Um, to bubble is the sound of boiling water, bub 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 bub, of other liquids. Is cinematopeic? Yes. Which with a classmate look up buzz, 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 buzz. Es como un zumbido, ¿no? El clip clap. A clip clap is when a horse is walking. That's a clip clap. Cock-a-doodle, no sé, cock-a-doodle-doo. Cock-a-doodle-doo es el cacareo. Cock, ¿ya? Meow, meow is, yeah, like meow of a cat. Um, Cecil had it here, I think. Uh, yes, Cecil, this is tricky. Chisporroteo, this one sparkles there, yes. Uh, Peter Potter is applied to a kid, yeah. I heard that Peter Potter uh, of tiny feet. I've heard this boy uh, mm, running around. Yes, I heard this Peter Potter um, of tiny feet. Yes, good. For example, putting sugar into a water is we are dissolving something. It's not a chemical change. Or when we freeze water to make ice cubes is a phase change, not a chemical change. Okay. We have here some other examples of chemical change in these cases. Yeah. So we're generating these bubbles when we, for example, put vinegar and carbon and powder soda. Yes, it's bicarbonate. Yeah, the iron rust when it's um, mixed with oxygen. Yes, with the air. Um, Instant cold compress. I'm not sure if you have seen these bags when you uh, bend it, you crack a substance that generate instant cold thing. Yeah, or fireflies. These are insects that are now very difficult to find because due to the light in the cities during night, this pollution of light, because we have light everywhere 24 hours even during night, so these insects generate light to find each other. Okay, to find each other and meet and copulate and generate more. They have an offspring. Yes. Um, so since there is so much light in the cities, they cannot meet each other. They cannot see each other because they don't recognize these small dots of light in the night, so they cannot meet each other and generate an offspring. Do you know what is an offspring? Generar crías, no? To understand and think, this first exercise. Specify whether a chemical change occurs in a following common phenomena, just justifying your answer based on whether or not a new substance appears. Cloud formation. New substance appear? No. We just see the water vapor coming together and form a cloud. Solution of sugar in water, no new substance is generated. We just dissolve sugar into water. Rust formation on a piece of iron, yes, as we have seen, we have iron and then we have iron oxide, as we saw in the formulation exercises before. Sugar caramelization in cooking. Good. Do we have a change of color? Yes. Therefore, and we have some vapor. It smells like the caramel of popcorns in the cinema, for example. Yes, these popcorns caramelized. The bronze statues that decorate some public squares have certain greenish color, unlike that the bronze. Yes, the bronze is like a copper color, but since it's in contact with oxygen, it start to change color to green. Yes, so we have a chemical reaction because of the oxygen. Food digestion's main objective is to transform food into nutrients. That is the physical or chemical change. Do we have some other chemical changes that occurs in our bodies? Explain it. Good. It's a chemical change because we could, for example, a protein, yes, and cut it in our digestion. We cut it in small pieces, and we obtain another substance, which are the building blocks, las partes pequeñas que forman la proteína. And these parts are called amino acids, aminoácidos. So we have a new substance. Okay. Do we have physical changes? Yes, because we are mixing. We are mixing the food with different liquids, and this is a change on the. For example, we have the bolus that we swallow, and then we have when we it mixed with some acids in the stomach, you dilute this bolus, so it changes uh, into more solid to more liquid. Yes, but it's not a chemical change from solid to liquid. It's just a change of state. Yeah, chemical is when you cut these big neutrons into smaller ones. Yes. Um, so another chemical changes that we obtain another thing. For example, when the mitochondria, uh, that is the organelle of the cell that generates energy. You give this organelle, you give them CO2, sorry, you give them sugar and oxygen, and you obtain CO2. That's why you exhale CO2. Yeah. Chemical reactions. Point two. You're doing good, okay? Thank you for being there. You're powerful, positive leaders. Um, Chemical reactions. It would be impossible to list all the chemical reactions going on around us. Chemical reactions occur constantly in our surroundings and our bodies. All these changes, although they involve the generation and disappearance of many substances we generate and other substances disappear, can be described as more or less complex set of chemical reactions. So, what's the definition of a chemical reaction? A chemical reaction occurs when starting a substance called reactants transform into other, I don't know what happens, other substances called products. Yes. And then this one, I don't know. Okay, good. That's the definition. That is the definition. Good. There are here some examples. Okay, for example, methane. Yes, is natural gas mainly. This is the farts of the cows and the gas generated when the trash, the garbage, is metabolized with bacteria. This smell is methane too, and this methane is used as a natural gas. Yeah, and we combine it with oxygen. It released carbon dioxide. Yes, the fumes, so it pollutes the air, and water vapor. Yes, and release in this change when it releases carbon dioxide and water, it releases also heat. That's how we heat, for example, the heater, la calefacción in casa, in our homes. Okay. So, why do new substances form? ¿Cómo se forman estas sustancias? In a chemical reaction, the appearance of new substances is due to rearrangement of the reactants atoms forming the products. This is very clear example here. We have methane, sorry. Sorry, hydrate yourself. Very good. Methane is 1 atom of carbon in black and 4 atoms of hydrogen. Yes. So when we match CO2 methane with two molecules of oxygen that are the reactants. Yeah, we rearrange these molecules and then we obtain some products. Yes, and heat is generated. Yes, it's exothermal. So this heat is used for, yes, heaters, to have a heater in, or the hot water when you have a shower with hot water. So this carbon, yes, can you see it in black, is here also, but is arranged with 2 atoms of oxygen. So we have 1 carbon and 2 oxygens, and then we have 1 oxygen with two hydrogens, and the other oxygen from here with the other 2 atoms of oxygen. Yes. So how many carbons do we have at the beginning as a reactant? 1 carbon, and 1 carbon as a product. How many atoms of oxygen do we have? 1, 2, 3, and 4. And as a product, 1, 2, 3, and 4. Yes, can you see it? And as reactants, we have 4 atoms of hydrogen. 1, 2, 3, and 4. And how many atoms of hydrogens do we have as a product? 1, 2, 3, and 4. Okay, simple as that. So we have here chemical reactions. So a chemical reaction is this one, but we're going to write it this way. Yes, this is the way we are going to write a chemical reaction or equation. Yes, CH4 plus 2 atoms of 2 with plus 2 molecules of O2. So this means 4 atoms of oxygen. We have one molecule of CO2 and 2 molecules of water. Yes, it's like here, 2 molecules of water, 1 molecule of CO2. Yes, yeah. So information about chemical reaction is written in a chemical equation. Yes, is written in a chemical equation. Okay, this is a chemical equation. Why we have chemical equation? Because it helps us to know how many molecules are there in the reaction. So how many molecules of methane do we need for a methane combustion? We need only 1 molecule of methane. And how many molecules of oxygen, of O2? 2 molecules of O2. And as a result, how many molecules of CO2 are generated? 1 molecule of CO2. And how many molecules of water? 2 molecules of water. Yes, simple as that. So this is a requirement. So the methane is not going to react with only 1 molecule of oxygen. We need 2 molecules of oxygen to make methane work as a reaction. Yeah? Good. Let's think. Using the formulas in the table here that we need to learn, okay? This is very simple. We went through it in the formulation topic. Water, H2O, carbon dioxide, CO2, oxygen, O2, hydrogen, H2, nitric oxide, yes, as methane, CH4, ammonia, NH3, sodium chloride, NaCl, sodium and chlorine, hydrochloric acid, and nitrogen. Yes, this is very common substances of very common molecules. Yes. Okay, something important here. Stoichiometric coefficient. This is the S number over here. This 2 and this 2. Yes, it give us information about how many molecules do we need in a certain reaction. Yes, and we separate the different molecules with a plus. Yes, and arrows, very important, that separates reactants from products. Yeah, good. Using the formulas in the table on this page, make diagrams like that on the preceding page on the following chemical reaction. 3 hydrogen molecules combine with a nitrogen molecule and form 2 new ammonia molecules. I will try to make a comment here. Okay, I will make a comment. I will write the formula I have here. So we have 3H2, yes, plus N2. This 2 is subindex when it's in the right side of the element of the atom. And then we have the arrow, and then we have as a result 2NH3, yes, ammonia. That's A. That's the A1. Yeah. What is the B? The B will be 2 molecules of hydrogen. 2 molecules of hydrogen combined with oxygen with only 1, yeah, molecule of oxygen. And as a result, we have how many molecules of water do we have? 2 molecules of water. 2H2O. Yes, H2O. 2 H2O. C will be 2 sodium atoms. Will be 2 sodium atoms. Yes, combined with 2 molecules. 2 molecules of C. No sé si así lo entendemos. 2. Así quizá lo entendáis mejor, ¿no? Yeah, I think it's better this way. And as a result, we have 2 molecules of salt, sodium chloride, and 1 molecule of hydrogen. Yes, that's it. Very good. And what about here? So we have a comment here, and we have here iron combines with atomic oxygen. Iron combines with atomic oxygen. Good. I don't know if I can close this. Yeah. Okay, now this comment will be 2 irons. Yes, I'm going to move it a bit here. I don't know if I can move it. Yeah. Well, then we will read it maybe this way. Yeah. 2 atoms of I'm going to move it here. Yeah. So 2 atoms of iron, yes, combines with atmospheric oxygen. Yeah. You suppose that is this one. Yes, 1 molecule of oxygen. And as a result, we have 2 oxide lo diré. Yes, iron oxide. Yes, simple as that. Iron combines with atomic oxygen. Yes, we have atomic oxygen. That's it. And that's it. Yeah, that's the final result. Yeah, and a 2 here. We can. So, can we have only this? Yeah, we can have it like that. Simple. The simpler, the better. So we have heat decomposed limestone into calcium oxide and carbon dioxide. Yes, this is A. Sorry, and this is exercise 5. I will put it here. And the B one will be limestone into calcium oxide and carbon dioxide. Yeah, simple as that. What will happen to this will be the 4th. Yeah, good. Yes, right. Write in words what this chemical reaction represents. Good. So, sorry. Yeah, this highlight. This highlight how we are going to write it down. Yes, 4 molecules of ammonia and 5 molecules of atmospheric oxygen as a reactant produce 4 molecules of nitrogen oxide and 6 molecules of water as a product of the reaction. Simple as that. Sorry, I'm afraid with pH. That's great. Thank you. That's it. Good. Next page, page 90. Very interesting. The properties of chemical reactions. Thank you for being there. Huh? You're doing great. The properties of chemical reactions. Yes. So chemical reactions have some important properties. This year we will focus on two laws. One related with masses of the reactants and products, and the other to the rate of a reaction, chemical reaction. So the law of conservation of mass. This is the first law we're going to learn. In a chemical reaction, matter is neither created or destroyed, only transformed. So the sum of masses of the reactants, yeah, is equal to the sum of masses of the products of the reaction. Yeah, very interesting. So in this reaction, the weight of the ammonia plus the oxygen is exactly the same. These two compounds, when they meet as a reactant, they are going to weight the same as the products here. Yes, the products the same as 4 molecules of nitrogen oxide and the 6 molecules of water. So this part of the equation is exactly weights exactly the same as the first part of the formula. Yes. So it says here we're going to discover the law of conservation of mass predates the atomic theory of matter. Yeah, that matter consists of atoms. This is a law drawn from experience. This is a law made by, so we can measure it really easily. So, for example, this is experimental proof. Yes, reaction involving gases was technically difficult to measure in that time, but in our time it's very easy. So we need, you can imagine, very easy to do, a scale, yeah, like this, a flask like this, a balloon like the red one, spatula or spoon to put the sodium bicarbonate and vinegar here in the same flask. Yeah. But how we do it? We put the carbonate soda into the balloon. Yes, and we put the vinegar with the yes, like the vinegar is here, and I have the balloon with the carbonate, and I uh, mm, join together. We put it together as in the picture, and the carbonate powder goes down, meets the vinegar, and the reaction is to generate CO2. So here in a scale, what we are going to see is that the weight doesn't change. Yes, it's the same as at the beginning. So what happens is that the matter stays there. It changes the form. So we have carbonate in the powder, and it's transformed into CO2. Yes, into a gas. A new compound is generated, CO2 is generated, CO2. Yes. So this is a very interesting law. The law of definite proportion. The masses of the reactant, yes, and the products maintain a constant proportion during chemical reactions. That means that here, for example, this is the only way we can make ammonia react. For example, can we react one nitrogen? Or I mean, this relationship is maintained. Yeah. So we have 4 molecules of ammonia and 5 oxygens. Yes, that's the proportion. and it's constant. To make them react is a constant proportion. Yes. So if we want to put less ammonia, less oxygen, but in the same proportion. So we need to divide all of them by the same. For example, if I divide it 4 by 4, is 1 ammonia, and this will be 5 divided by 4 oxygens. 1 as a reaction, we will obtain 1 nitrogen oxide, because we have divided all of the 1, 2, 3, and 4, all of the components of the reaction. We have made them divided by 4. So this will be 6 between 4. What I meant is that the proportions are always the same. Yes? That's the thing. That's the formula. The rate of change. We can establish the rate in which chemical reaction occurs by measuring the time. Okay, measuring the time that takes that the products to react will appear in the reactions disappear. Yes, so it lasts 4 minutes, 4 minutes, always. Yeah, if we maintain the same, of course, the same characteristics in the lab. Normally, when we put the reaction into a fire or to give them a little bit of heat, the reactions can occur easily. Yes, good. Temperature. In general, we can see the increasing in temperature of the reaction. Normally, most of the reaction generate heat. Yeah, like burning a paper or burning the methane, yes, natural gas, concentration of reactants. The greater the concentration of the reactants, the faster the rate of reaction, yes. We have a limit, of course, of reaction, but more reactions, so for example, more paper you have, and more oxygen you blow to a fire, the reaction will be faster. Yes, the rate of the reaction will be faster. The same as with temperature normally. Okay, we have a problem solved here. Okay, thank you for. I think it's very clear. These 3 laws are very simple. I will remind it again. The law of conservation of mass, the same mass as a reactant, the same mass as a product. The law of definite proportions, we have always the same proportions between reactants and the same proportion between products. Okay, the rate normally is the same rate. It lasts, the reaction, it lasts the same, dura lo mismo. How we can speed the reaction, we put more reactants. Okay, ponemos más productos, ¿no? Más, pues se quema más rápido, ¿no? Como ponemos más leña, se quema antes, ¿no? Más calor. So here we have a problem solved. When 30 grams of nitrogen reacts with hydrogen, we obtain 170 grams of ammonia. What is the mass of the hydrogen that reacted? What mass of ammonia would form if we had 90 grams of nitrogen reacted? To calculate the mass of the hydrogen that reacted, we assume that the law of conservation of mass is satisfied. Yes, so mass of the reactants is the same as mass of the products. Yes, so the mass of the hydrogen is different between the mass of ammonia and the nitrogen. Yes, so in our reactions like this, I'm going to put nitrogen reacts with hydrogen. We obtain ammonia. Yes, here I will write it. So this is the proportion. Yes, we have nitrogen plus hydrogen equals NH3. Yes, this is ammonia. That's the main result. Yeah, that's the main formula. With stoichiometric values, it will be like this: 3, and then no, and then 2. These are the stoichiometric values. 3 Na2. So because here is saying, sorry, me he equivocado. Esto no es nada, jolín. Esto no es nada y esto es 3. Ahora sí. Very good. Yeah, that's it. So we have that nitrogen is 30 grams. This is 30 grams. Plus hydrogen, well, we don't know, is 170 grams. Yes, simple as that. That's it. So what we need to do is esto, ¿qué va a ser? Minus 30 grams. Yeah. So that's the value of hydrogen. Very simple. Yeah. So this 170 minus 30, that goes from the one side of the equation to the other side, 100 grams of hydrogen. Yeah, very good. Now this part is, we have a proportional rule, yes? So if 30 grams of nitrogen generate 70 grams, 90 grams will generate, 90 grams of hydrogen generates 510 grams of ammonia. Yes, 90 multiplied by 170 divided by 30. Very easy. Research information about the chemical reaction between vinegar and sodium bicarbonate that we propose you use to check the law of conservation of mass. Then answer the question: which chemicals are the reactants and products of the reaction? Yes, which chemicals? Yeah. So, which chemicals are the reactants? Chemicals of the reactants. The chemicals of the reactants, I will write it here, is NaHCOO3. That's sodium carbonate. Yes, that's a reaction. And vinegar is this: CH3COOOH. Like this is vinegar. And we have as a result, I'm going to NaCH3OO plus CO2 plus H2O. Yes, that's it. This is the reaction. So they're asking me, what are the chemicals? Yes. What does the balloon inflate? Why does the balloon inflate? Because we have CO2. Yes. So here, due to the CO2. Yes, more formal. Due to. Yes, good. Next, why does the experiment test whether glass have a mass? gases have a mass. To demonstrate that is a chemical reaction and the law of conservation of matter is true. That's it, yeah? Demonstrate, yes, good. If this is 92, 91, good. Very interesting. If 224 grams of iron reacts with oxygen forming iron oxide, how much iron oxide will 112 grams of iron produce? Very interesting. How good. So the thing is, how much iron oxide will 112 grams of iron produce? So we have as a reaction, we have this. Yes. For example, and we know that 22 grams plus oxygen, we don't know what it is, how much, generates 100, forming this 3 grams of iron oxide, yeah? Iron oxide, and then how much iron oxide would 112 grams of iron produce? So if we have 112 grams plus this, the weight of the oxygen, we don't know how many grams of iron we will produce. If we realize it's half of it, so it will be the half of 320, yes, which is grams of, yes, I just divided between 2. Yes, they're asking me 220 and 24 grams, produce 320, so I divided by 2, la mitad de 200, ¿qué me dicen? ¿Cuántos gramos de hierro producen, cuántos gramos de óxido de hierro producen 112 gramos de hierro solo? Pues si yo sé que 224 crean 220, pues la mitad de 224 creará la mitad de 320, ¿vale? Very good. Ninth exercise. Why do you think that most forms of cooking involve rising food temperature? Due to the rise of activation temperature. Yes. So molecules are moving more and are more likely to react. Very good. And yes, explain why storing food in the refrigerator conservates. Okay, good. This is low temperature will decrease the metabolism of bacteria. Yes, So metabolism of bacteria, they cannot eat the food because um, uh, they cannot um, metabolize, yes, because of the temperature. Good. And next, fourth, good, chemical. This is very interesting stuff, natural and artificial. This is very interesting. A synthetic reaction is aim of obtaining or manufacturing a substance. So it's made by us, yes? Um, synthesis, sorry, it's not made by us. It comes naturally, okay? For example, when you put the bread and it's decomposed by bacteria and fungi, yes? Cuando se descompone el pan, this is a natural reaction, yes? We are transforming substance into another, yes? And is made by living organisms produce substance they need, such as protein or ribosomes. That's an example of things that are in the cell. You're doing good, okay? You're doing good. Let's go. The chemical industry also uses many artificial synthesis reactions to obtain substances and products that cannot be found in nature. So, these are artificial. We're using synthesis reactions in our lab made by our technology. Yes, chemical industry have made medicines or drugs. Have made uh, different synthetic plastics, solvents, fibers like nylon or polyester. Yeah, and it's made by fuel, by petrol stuff. Yeah, we can make diesel, and fuel is a raw material. Raw material is materia natural, una materia en crudo. And it's manufactured. Sorry, is manufactured. Yes. And other products. Besides those already mentioned, the chemical industry produces many products like fertilizer, acids, additives for construction, food additives, and other. Yes, this is a chemical, a pharmaceutical, like chemicals used in drugs for helping us to fight against the coronavirus, for example. We need fuel like diesel and chemical like plastics and everything, yes? So, natural and artificial products. Sometimes we hear the claim that something is better or less harmful to health because it's natural. Therefore, most food additives have a bad reputation. Although some are natural and some medications advise that its natural remedies are more popular than mainstream medicines. Whether a product is natural or artificial, synthetic, might have nothing to do with whether it benefits society or the environment. Here are some examples. Recycled plastic bags are a problem for the environment. Now there are bags made of potato starch, yes, that decomposed. The flavor of vanilla comes from a substance called vanillin, found in vanilla pods. Extracting it is expensive, so it is synthesized from lignin. And lignin is a substance generated by plants, yeah, and it's very sticky, sticky pegajosa, and a substance that is found in wood and easier to extract. Yes, very interesting. Now, write down the composition of some of the clothing you have at home and specify whether the fibers are natural or synthetic. Which fiber do you have more of? What do you think it is? Yeah. And okay, I'm going to show you a very interesting thing, which is the also a website, and also search for information about shopping bags and the meaning of terms biodegradable, compostable, and recycle. From the above information, say how people should use each type of bag to minimize pollution. Good. We shouldn't use bags as much as we're doing because they last for 5 minutes to take the food from the store to your fridge, and this bag goes to the to a dam, ¿vale? Un vertedero, or they recycle. Yes. Some stores, they are selling, like Lidl, when you put the fruit, is a compostable bag, which means that is when you put it in a dam, ¿vale? En un vertedero, or in the ground, it decomposes easily, okay? Which means that it's made out of, like it's here, starch, ¿vale? Almidón de patata. And some other stores, they are using plastic recycle, okay? So you put the plastic bags and they are recycled to generate more bags, plastic bags, but they're still plastic, okay? Even though it's recycled, they can end up in the field or in the sea. Yes, I will show you here a website that is very, very interesting. Good. This is the data about plastic stuff. Yeah. I will show you this. Is very interesting. Yes, plastic pollution is a world in data, or world in data.org, and this is the pathway, el camino que siguen el plástico que entra a los océanos, ¿vale? This is the global, this is an industry that generates 270 million tons per year. 270 millones de toneladas de plástico cada año. ¿Vale? Y el plástico que se genera cada año es 270 millones más otros 5 de productos que se han acumulado del año anterior, 5 millones más. And then what goes, this global plastic waste, 270 million tons per year. It can exceed primary production a given year, since it can incorporate production from previous years. Yes, coastal plastic waste. Yes, almost 100 million of tons in the houses close to the sea. Yes, 50 kilometers from the coast. So at the end, what happens is that plastic inputs to the ocean is 8 million tons per year. 8 millones de toneladas. ¿Vale? 8 millones de toneladas. So it means that we are putting 280 million of tons of plastic under the earth. In a dam, en un vertedero, 270 millones de toneladas de plástico al año bajo la tierra. Y ahí se supone que se irán degradando. El plástico tarda entre 100 años, 200 o hasta 500 años. El plástico en degradarse. So, this is the production of millions of tons per year in 2015. Let's see how much tons we are anualmente, cada año, hemos producido desde 1950. Sorry. In 1950, only 2 million of tons. Yes, only 50 years ago, only 2 million of tons were made out of plastics. Yeah, what happens later on? In 1, aquí lo dice, 1973, 51 millones de toneladas. Yes. In comparison with this is our maximum. Yes, 350 million is what is made out. Okay, so sorry, I don't know what happened. Sorry. Good. Next. Okay, 90. Here you can see it. Accumulate global plastic production. Yes, we have been accumulating plastics from the 50s. Here we are accumulated in the world in 2015, 7.8 billion of tons accumulated. Yes. So here is, we have increased the recycled plastic. We have increased from every year we are increasing it, but is only in 2015, 20% of the plastic is recycled. Yes, the 80% rest is even incinerated, burned, or 50% is discarded into under the earth or in the ocean. Yeah, good. This is a graph, very interesting one, because it shows that only a tiny part of the plastic is recycled. Yes, and what does it mean is that we are saving only 100 million tons. 100 million tons. Yeah. Of recycled plastic, but just for some time. Just for some time. Because at the end, what we are putting into the garbage is a vast amount of plastic, 4,600 million tons. That's a lot. So recycling is not the solution. We need to stop using plastic that much. This is something you, as future citizens, you need to solve. Okay. So this is a very interesting one. Primary plastic production. Yes. So the most plastic generated is packaging. Okay. I have packaging like this. This is vitamin C in plastic. This is a package. Yes. Building and constructions. Yes, construction like the buildings. Yes, the windows and everything. Other sectors, textiles, 47 million. This is the fourth main source of plastic, or clothes. Yes, to make these clothes elastic is made of plastic. Yeah, and it lasts I don't know 2 years, and then you throw it away. More plastic. Yeah, more plastic. Plastic waste de toda la basura, del plástico que se tira a la basura, 141 millones de toneladas solo de paquetes de estos. Other sectors, all the rest. Textile is the third source of pollution of plastic. Yeah, Which countries pollute the more uh, per person? So we have, for example, Germany that has a lot. Um, every day, half of kilo of plastic is thrown uh, to the garbage. Here is 300 300 grams of plastic per day. Yes, look at is United States, okay, but this is amazing. Germany, that is supposed to be very environmentally friendly, or Ireland, almost half a kilo. Yes, and Guyana, a lot of plastic. Yeah, a lot. And so this is a very interesting chart. Yeah, United States, United Kingdom, Brazil, China, Canada, or India. Yes, and a country, let's say Spain. Yeah, where is Spain? Yeah, under the United States, we are generated a lot of a lot of plastic. Let's add Germany. These Germans, wow, almost half a kilo. That's a lot, man. That's a lot. Total plastic by country. But even though China is generating few kilos per person, what we have here is that a lot of that is generated by China. Yes, a lot. Germany, a lot. United States, a lot. Brazil, a lot. Yes, the larger countries, of course, are the ones that generate more plastic. Yes, we have Germany, United States, China, Egypt, India. Very interesting. Share of plastic waste that is inadequately managed. Can you see here a lot of plastic is just burned or thrown into the water, or can pollute um, the environment. Yes, the rich countries are in a way managing the plastic. Yeah, so the countries that pollute more, India and Africa. Yes. Good. Share global mismanage. China, they don't manage plastic at all. Pretty bad. And well, in things that we need to coming back to our presentation, the book. Search information about Formica. Okay, and I wanna can we improve quality? Yeah. Let's see. Formica here. It's just plastic. Originally is laminated composed material embedded by Windsor Electric Corporation. So there's a lot of laminates of plastic in a high pressure. Okay. Um, Search about vanillin. Vanillin is this compound. This is the original one. Yes, with this group, but they add this other group. Okay, to the compound to make it more. Um, it smells more of vanilla, and you don't need to grow vanillas flowers. Okay, you just do it in the lab. And um, this is the salicylic acid. Yeah, and they're asking what for what medicine is salicylic acid to main active ingredient. So The main active ingredient is ácido acetil salicílico, que viene del... ¿Esto está en español? Ah, está en español. Bueno, ácido acetil salicílico, como aspirina, para el dolor, la fiebre, la inflamación, etc. What benefit did modifying provide? Explain your answer. Benefit did modifying that. So it comes from the original one, the silicates of the cork of the tree of Salix, el sauce, and so it's made the ácido acetil salicílico healthier for your stomach, because the original one made your stomach having some problems in the inside, yes, generating some kind of ulcers, yes. But still, ácido acetil salicílico was better, but I don't think it's a good option, okay? Because it causes, for example, in females, because the blood is too liquid, so when they have the period, they can have problems in the coagulation of the blood, okay? And that's it. Sorry. Then again, this one. Okay, so what's the geographical location? The white willow, is all over Europe, very easy to get. Okay. Chemical improves quality of life. Well, I'm not sure about that. Okay, environmental chemistry deals primarily with identifying the time of amount of pollutants in the environment. Environment chemists study both the source of emission and how to other pollutants reach other places. So they measure the pollution and try to solve it. And sustainable chemistry makes deals and design environmentally friendly products. So we are going to decide a product that is environmentally friendly. So that doesn't generate any substance, or generate as less pollutants as possible. See the picture, manufacturing. Yes, thanks to sustainable chemistry, manufacturing processes that emitted pollutants are being replaced by others with less waste products. See the picture below. Okay, so this is the original industry, and this is the nowadays industry. Okay, so things we need to remember of this is that we have some chemistry that studies how to help environment and solve pollutants and how to get rid of these pollutants, and we have a chemistry that is between quotations, we might say that they try to be as less harmful as possible, ¿vale? Intentan ser los menos contaminantes posibles, ¿vale? Pero no lo consiguen, ¿vale? Os voy a recomendar that this is a film, Dark Waters, that is talking about the consequences of PFOA. PFOA is this is the coat, ¿vale? O lo que se llama teflón, ¿vale? Que es lo que se pone en las sartenes, okay? In the pans. So some industries like this PFOA free, so no tiene el teflón. El teflón Esta película habla del teflón, de esta empresa, DuPont, ¿vale? DuPont, que generó el teflón y que causó daños en las personas. Sorry, it caused some damage in the persons that were living close to the industry. Yes, this marvelous industry was very pollutant, very, and was poisoning people around the factory. And this film, Dark Waters, very interesting, is talking about this lawyer that was defending the citizens of the town where the industry was located. Okay, so some deformations were taking place in the city, and a lot of death of cancer in a city of United States. Yes, and this lawyer that is about this. The film is about this lawyer managed to put DuPont into a court and sue them, las denunció, and this is what they get. DuPont paid 10 millones de dólares a los afectados, ¿vale? Afectados, que fueron miles de personas. Y que y los trabajos de limpieza y gestión de los residuos del PFOA o EPA fueron 6 millones de euros, ¿vale? Entonces, thanks to this lawyer, this is the real one, and this is the actor. Very good film you need to watch. So, as this company, there are thousands of companies. For example, we have the largest companies like bisphenol A, and this is the bisphenol A is a very, very dangerous product. Is in the sorry, voy a poner aquí imágenes. Is in plastics everywhere, and we have here in Spain the largest industry to generate this poison. Here in Spain, we are generating this kind of plastic, which is very dangerous for pregnant women and for kids. So, coming back to our topics, we have these questions. Search among medicines in your home, ingredients that can be obtained naturally or synthetically. Very difficult. But I want to talk about so analyze the picture below. Do you think this type of companies that seems very luxury and oh my god, very doesn't mean that they're operating good, as we saw in DuPont and PFOA, Teflon stuff were doing. Yes. So, for example, I'm going to talk about soap and detergent. Yes, soap and detergent are causing this. I'm not sure if you're watching this. Okay. This is the water, and this inside the water we have fishes, aquatic biome, which means we have plants, mollusks, crustaceans, and we put a lot of foam in the surface. Yes, in the surface. Well, so it's very difficult for the light to reach the plants here in the water, algae and plants. So they are not generating oxygen. So what happens is that this biome is destroyed, okay, because there are no light coming to the water, and the plants cannot do photosynthesis, and they cannot generate oxygen. Yes. So, and most of the detergents have phosphates, and also los fertilizantes artificiales de las plantas, de las huertas, van al agua, generan una capa, que se genera una capa de algas en la parte superficial y no deja pasar la luz, no se hace la fotosíntesis en el agua y está muriendo toda la biodiversidad. Esto es lo que está pasando en Murcia. So this sea, small sea, that is in La Manga, is dying because we are generating so much pollutants that are in the surface that the light cannot get in. The same happens with the oil, yes, that is in the surface. So what's the solution? We need to clean this kind of water, and when we waste the water after cleaning it, could be better for our rivers and to our seas. Yes. Good. This was talking about soap and detergent. Different films obtained by petroleum, a lot, diesel, and everything. So we are fertilizers, as I said, very dangerous. They generate a phosphate layer, and the algae don't block the sun to go inside of the water. Plastics, like a lot, we're generating it. We are generating drugs, that's the good stuff, especially when we have coronavirus. Detergents, very poison if they use phosphates, and petrol. And so we have a large additives in the food, preserving it from deterioration. And I'm going to talk this last point about the destruction of ozone layer. So I have here how the ozone layer works. Okay, this is the visible light, so we cannot see. Oh my God, the ozone layer is blocking the light. No, it's blocking specifically the UV rays that protects us from cancer, skin cancer from the sun. But it doesn't block the UVA. Yes, so plants can do the photosynthesis. Yes. So what's the problem with this is and what's the difference between the ozone, and when we are destroying the ozone layer is now very good, in good shape. Did you know that we have a hole in the North Pole, but is generating quite good. So what we need to learn here is the reaction. Okay, very easy. Oxygen with UV rays is divided in two, and this simple atom meets another one with two and generates ozone. Yes, so every atom of oxygen split it in two, we have three. Yes, this occurs when we put also NO, óxidos de nitrógeno generados por el diésel, la contaminación, ¿vale? De los coches diésel. Entonces se está produciendo un ozono troposférico, que es esto de aquí, ¿vale? El oxígeno más los compuestos volátiles, contaminación básicamente, más rayos UVA, se genera el ozono troposférico en esta zona, ¿vale? El ozono in this area. The ozone layer should be at 80 kilometers above. Yeah, okay. We're living here. The planes are here in 2 kilometers. sorry, 10 kilometers above, but ozone layer is 80. 80 is here. The ozone layer should be here, not here. When we have this ozone here in this, we have ozone generating in this reaction in the tropospheric, en donde nosotros vivimos. This is toxic. Ozone is toxic. Okay. Good. How the whole of ozone layer is made? Is due to CFCs, chlorofluorocarbonados. And so chlorine fluorocarbonides. So what we have here is 1 carbon, 3 chlorines, and yes, 3 chlorines and 1, I think it is hydrogen. So when these CFCs that it was in the air conditioning, los aires acondicionados, they have it. The fridge, the neveras, they have this gas. So when they free this gas and meet the UV rays, we have chlorine. And chlorine in 80 kilometers above the atmosphere breaks down the oxygen. So the chlorine is very likely to meet the oxygen, 1 atom only. So break the 3 atom molecule of oxygen. So we have chlorine oxide and oxygen. And this one, again, meets another oxygen from another reaction, and ping, the chlorine is free again. It's free again to destroy another molecule of ozone. So what happens is that it's a chain reaction. So it's very difficult to stop, to break down a hole. So what happens with the chlorine is that it goes 80 kilometers above our heads to destroy the ozone layer. The chlorine goes really up. It's very light. It goes really up and destroy the ozone layer 80 kilometers above our heads. Because some people think, okay, to destroy the ozone layer, here, the ozone here in the tropospheric layer, to destroy the ozone that we breathe and is toxic if we breathe it, we can free the chlorine and destroy the oxygen. Yes, but chlorine goes really up, doesn't stay here. Chlorine goes really up, really easily go up, and it reaches this area here. Okay, good. This is the reaction, very simple. So the greenhouse effect is this one, greenhouse effect. So this is a natural one. I'm not sure if I can. This is the bigger I can get. So we have greenhouse gases, GHGs, absorben la radiación infrarroja, nada que ver con la ultravioleta, ¿vale? So this is an example. We have a car in the sun, okay, with the windows up, okay. So in summer, the infrared from the sun gets in, heat the inside like an oven. The heat doesn't go out because we have the windows, yes? So the windows are the greenhouse effect, yes? You know that the glass of the windows of the car doesn't allow the UV rays to get in, yes? But it doesn't stop, the windows doesn't stop the heat of the sun to warm the interior of the car, yes? So the windows are up, the infrared rays are coming in, and the interior of the car is heating up. Yes, this is the greenhouse effect. So the greenhouse effect is like putting all the windows, all the glass covering our world. So the heat, the infrared can get in but not go out. So it's like having a glass that is surrounding the earth. So the heat cannot go out to the space. Yes, if you can see here, the arrow are really gross here, and this thick, and this is really thin, muy pequeñita. Yes, casi muy poca energía calórica se puede desechar porque here we have a layer that don't allow the heat to go to the space. Yes, this is an enhanced human green effect. Carbon dioxide is produced by burning fossil fuels like CO2. Traps additional heat, como que atrapa el calor del infrarrojo, inside the lower atmosphere, rising the Earth's temperature above what it would otherwise be. This is very interesting because this graphic is made up by Boeing, these airplanes that are consuming a lot of fuel, and they are they are putting a lot of CO2 in the atmosphere. Here we have an article about el transporte aéreo aumentó un 25% sus emisiones de gas invernadero en 4 años, on only 4 years. So if this overuse of planes that are very pollutant, continues this way, these are going to have a problem. So here we have a ministry that is talking about this problem. Dice, las emisiones de transporte en España en el 2004 fueron de, bueno, muchísimas toneladas de CO2, habiéndose casi incrementado un 50% desde 1990. El protocolo de Kioto decía que solo podíamos crecer un 15% y hemos crecido un 30% nuestras emisiones. Luego tenemos que hacer algo, ¿no? Y se ha incrementado la demanda de movilidad de pasajeros. No obstante, en 2007 se ha registrado una disminución por la crisis, igual que la del coronavirus, que va a causar pues que vamos a dar un respiro a la Tierra porque estamos moviéndonos menos y contaminando menos. El sector del transporte representa un 25% de las emisiones y un 40% de las emisiones de sectores difusos como la industria, ¿no? Y la carretera supone el 95% de las emisiones, ¿vale? Así que, bueno, pues se están haciendo acciones para disminuir las emisiones, ¿ok? Very good. So, this is the greenhouse effect. Acid rain is phenomenal. This is not happening anymore because we are not emitting SO2 that much. This SO2 was generated burning coal, cuando vertíamos, o sea, quemábamos carbón. And we are not doing that much, so no sulfuric acid is emitted, yes? We're still emitting some others, but acid rain is not a problem anymore. The problem is this ozone that we are breathing and NOx that we are breathing from the diesel cars. That is very carcinogenous, is very toxic, okay? And we need to stop using this kind of cars and move to the electric ones. Like, for example, they are doing here, so the government, sorry, it's not here, it's here. So they are putting a lot of money to invest in economía sostenible, presupuesto general del Estado, planes Mobile, compra de vehículos eléctricos. So I hope we can improve that in the future. So okay, exercises we need to solve to finish this topic is page 100 is this 8 and 9. Okay, 8 and 9. So we have the mass iron oxide form will da 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 da. Come on, we're finishing. You're doing great. Okay, good. So the thing is, we need we have 224 grams of iron, which combines with oxygen to form iron oxide. Are the following statements true or false? The mass of iron oxide formed will be the sum of 224 grams plus the mass of oxygen. Yes, that's true. A is true. B, the mass of iron oxide will be less than the iron at the start. Of course not, because we have iron plus oxygen, iron oxide. So false. Iron oxide will be more than the iron by itself. Yes. C, the mass of iron oxide will be the same as the iron? No, will be more, because we have iron and oxygen. And then we have iron oxide. Yes? I will write it here. Yes? So, false. 9. 8 grams of hydrogen reacts with 64 grams of oxygen and forms 72 grams of water. Yes, hydrogen and oxygen. Check that the reaction follows the law of conservation of mass. 8, and let's see, this is all right. Is it true? Let's see. And we have hydrogen plus oxygen. We have water. Yes. Yep. So we have here we have a 2, and that's it. Okay. Good. So we have 8 grams plus 64 is 72 grams. Is it all right? Because 64 plus 8 is 72 grams. So all right, is true. Yes, A is true. It's true. Yeah. Conservation, the law of conservation of mass. Calculate the mass of water. Okay. B, calculate the mass of water that would form if we have 20 grams of hydrogen from full reacted. Okay. Very, very interesting. We have tenemos 20 gramos de oxígeno. Si 8 generan 72, 20 grams of hydrogen generarán, we don't know. So this will be 20 multiplied by 72 divided by 8 is equal to Yes, it's true, 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 true. So that's it. This is the explanation of this topic. I hope you enjoyed. You have been doing really good. I hope you enjoyed the information. This is too much, but you can stop the video. I did it in just in once, just for make it more uh, to flow with the knowledge and with the pictures, with the information of plastics, and so on and so forth. Yes. Um, okay. Thank you very much for being there. You're wonderful, positive leaders. You know that. Okay. Bye.